I'd like to present one paper. The title is Passive Motion Analysis of Two Identical Regular Octagonal Objects that Move on Passively Vibrating Tilted Stage. I am Fumihiko Asano from JIST Japan, and this paper was co-authored by Isao, Tokuda, and Longchuan. And we are aiming to develop an advanced carrier system or object transporting system that can automatically align and sort a large number of transport objects whose outer shape and mass have a non-negligible level of influence on their own motion characteristics. In our previous work, it was numerically confirmed that the moving speed of the regular octagonal object or regular rimless fluid moving on a tilted stage can be actively controlled in the vertical direction based on the effect of entrainment. This is our previous simulation. And this is our prototype experimental system. By utilizing the active rimless fluid as an actuator, and this is also rimless fluid, but this is passive, and this is a transporting object. So again, by using the active rimless fluid as an actuator and vibrating the stage up and down, the moving speed of the passive rimless fluid can be controlled by utilizing the effect of entrainment. However, the feasibility of motion control when the number of the object is increased remains for future study. So in this paper, we'd like to discuss the case of multiple object. As a basic study of it, in this paper, we investigate the phase relationship of passive dynamic working motions generated by two identical regular octagonal objects that move on a non-powered, flexible, and inclined stage. The octagonal object has the same dynamics as an 8-legged rimless wheel, and the equations of motion and collision are specified as a 3DOF rigid body. And the equation of motion of the tilted stage is also specified as a 1DOF spring mass damper system. The two objects generate passive dynamic motions only by using the action of gravity, and the effect of the motion and collision of them affect each other through the tilted stage. This system can be a basic model of a non-powered object transporting system, as well as a simplified model of the movement of multiple people working on vibrating structures, such as suspension bridges and floating islands. We then conduct numerical simulations to show that the whole 7DOF system can generate stable motions with a suitable parameter setting, but the phase relationship between the two objects differs depending on the initial state. We set the generalized coordinate variables x1, z1, theta1 for rimless fluid 1, the rear walker and rear object, and the forward object rimless fluid 2, x2, g2, and theta2. The modeling, let qj be the generalized coordinate vector of rimless fluid j, and xj, dj is the contact position stance foot of rimless fluid j with the stage, and theta j is the angle from the normal direction of the slope, and phi, here phi is the tilted angle of the stage. The equation of motion of rimless fluid j then becomes like this. And the equation of motion, we assume that the stage is infinitely long and has uniform dynamic characteristics regardless of the position of rimless fluid j moving on it. And let ZF, ZF is here. So ZF be the z position of the stage. So the z direction dynamics of the passive tilted stage is then modeled as the following simple mass spring damper system. Here, g0 is the natural length of the spring. So equation of motion of the augmented system. Let Q be the generalized coordinate vector of the augmented system. It includes Q1, Q2, and GF. Then the equation of motion of the augmented system becomes like this. Here, JC transpose lambda C is the holonomic constraint force vector. The Jacobian Jij, this is for impact, is determined according to the condition that the rimless fluid J has a complete inelastic collision with the tilted stage. So this is a holonomic constraint condition immediately after impact. And the dynamical effect of the collision of one rimless fluid is transmitted to the other rimless fluid via the vibrating stage. And by repeating this, the movement of each other are gradually synchronized. I will show you the simulation. First, we set theta 1.0 equals 0.1 radian per second. The tilted angle is 0.10 radian. Although it is hardly visible visually, the tilted stage is vibrating slightly, and the two rimless fluids synchronized each other. Simulation results. We set the initial state like this. Theta 1.0 was 0.1, whereas theta 2.0 was always there in this paper. The system parameters were chosen as the values listed in table 1. And from the simulation results, we can see that the collision of rimless fluid 2 occurred immediately after the collision of rimless fluid 1. And both step period converged to the same value. So they are synchronized. Okay. I will show you next simulation results. We then increased the theta 1.0 to 1.0 radian per second, a little faster than the previous one. So in this case, the two rimless fluids were also synchronized to each other, and the stage was also vibrating. And this is the simulation results. We can see that the step periods of both rimless fluids, rimless fluids converged to the same value again, but the phase relationship was reversed. We can see that the collision of rimless fluid 1 occurred immediately after the collision of rimless fluid 2. This means that the mutual phase relationship is determined according to the initial angular velocities of rimless fluids. And next, we then investigate the effect of initial angular velocity in more detail by introducing the evaluation indexes related to time, as shown in this figure. Here, T1 and T2 are the steady step periods of rimless fluid 1 and rimless fluid 2, and delta T12 is the steady value obtained by subtracting the latest collision time of rimless fluid 2 from the collision time of rimless fluid 1, whereas delta T21 is the steady value obtained by subtracting the latest collision time of rimless fluid 1 from the collision time of rimless fluid 2. And calculation procedure. In this paper, we numerically investigated the effect of the initial angular velocity on the phase difference between the two rimless fluids. The calculation procedure for the evaluation indexes is shown in this algorithm. And analysis result. This figure, figure 5, shows the analysis results of the evaluation indexes where phi equals 0.12 radian and phi equals 0.20 radian. In each case, we can see that the phase relationships of two rimless fluids alternate as θ1.0 increases. And in both rimless fluids, the step periods converge to the same value, but the phase relationship changes in a complicated manner according to θ1.0. Regardless of the conditions, the step periods of two rimless fluids, two objects on two rimless fluids always converge to the same value, and this relationship holds. Next, the effect of viscosity of the stage. So the viscosity of the stage has a great influence on the stability of the motion of the object moving on it. Next, we observe and analyze the change of the phase relationship while gradually reducing only the viscosity of the stage. So this is a calculation procedure. So we firstly set the initial condition to these values. And after that, we gradually decrease the value of the viscous coefficient CF. And we finally calculate the T1, T2, delta T1, 2, and delta T2, 2, 1. Figure 6 shows the analysis results of the evaluation indexes with respect to CF, where phi equals 0.12 radian and phi equals 0.20 radian. The phase relationship of the two rimless fluids does not change over the entire range of CF. That is, delta T12 is always longer than the delta T21. So there is a magnitude relation. And when CF is the range about 8,000 from about 8,000 to 2,000. The values of delta T12 and delta T21 don't change while maintaining an almost constant value. And this implies that symmetric motions are generated along the time axis. And in each case, this relationship holds. So when CF becomes smaller than 2000 in each case, the phase relationship begins to be biased, and the collision time difference between the two rimless fluids is gradually approaching. Okay. Sorry, conclusion. Yes, conclusion and future work. And in this paper, we conducted a basic motion analysis of passive rimless fluids that move on passively vibrating stage. And we discussed the phase synchronization with respect to the system parameters. And in the future, we will conduct more detailed analysis by changing the system parameters. So that's all. Thank you very much for your attention.
Okay. Thank you, Fumihiko, for your presentation. Questions from the audience, please? No questions? Okay, I have a question. Well, in your model, you work with the same mass for both octagonal objects, right?
Yeah.
In a real situation, I'm sure that you will have difference between the masses for each one. Well, what do you think that will happen when your masses are different? Have you tried to simulate this situation or not?
Yes, thank you for your interesting question. We have already conducted some test simulation by changing the mass or the radius of the object. So if their physical parameters are slightly different, but they can synchronize each other. But if the difference is very large, significantly large, so for example, one is 2 kilograms and the other is 1 kilogram, then they cannot synchronize. If the difference is about 10%, they can synchronize. So
okay.
It's very interesting phenomenon has been observed. We will report in the future paper.
Okay, Thank you. Thank you very much for your answer.
Right.
And is there any other question? If no, if not, okay. So thank you again, Fumihiko, for your presentation.